We're going to continue by now starting to look at tools to understand the quality of our model and our classifiers. And so the first quantity that we can look at is defined as the accuracy of the model. It's the most basic metric that we use to evaluate classifiers. It's fairly widely used. Scikit-learn has a tool in it. Every model object in Scikit-learn, they all have very uniform API. And if you call the score method in Scikit-learn, you will get exactly this quantity computed. And it is a quantity that is very sensitive to the threshold. But as we'll see in a minute, accuracy, even though intuitively it looks like a perfectly reasonable quantity, and it's in fact a useful metric to look at, it's not the end of the story, and it can actually be fairly misleading in actually pretty common examples. So the basic definition of accuracy is that we ask, what is the ratio between how many observations did we classify correctly versus how many were there? So seems like a very reasonable definition. I'm making n, I have n data points. How many of them did I get right? And so you would imagine that having high accuracy is a good idea, and having low accuracy is a bad idea. And that's not false. But it's not the end of the story, and we can see the pitfalls of this definition, or the limitations rather, because it's not that it's incorrect, it's that it has limitations, with a very important and real-world example that is actually a common use case. Let's imagine that we're trying to build a classifier for spam, for email, right? And since what we are trying to predict is this email spam? That's our 1 class. And the it's not spam, what we call ham, is the 0 class. So let's imagine that our testing data set has 100 emails, but in general, most people get more real email than spam. We all get spam, but we tend to get more real email. So it's not uncommon to have a data set that has more of ham than spam in this case, right? A small amount of spam. Let's imagine that we have in our data set of 100 emails, 5 of them are spam, and the remaining 95 are ham. And so now let's think about a hypothetical friend of yours who has not taken data 100 and suggests, hey, I can do this, just classify every email as ham. Literally, like, your classifier is very simple. For every incoming email, it says it's not spam. That's it. Pause the video for a second and think. What will be the accuracy, as per the definition we just saw, of this classifier, of your friend's classifier? And is that a good idea? Do you think that based on that, do you think this is a good model? Is it useful as a model? And what do you think then about accuracy in this context? So pause for a second, think about that. So the accuracy of this model is 95%, because by definition, it says that everything is ham. 95 of those emails are indeed ham. So we got 95 of them correct. We had 100 in total. It's 95 out of 100. That's a 95% accuracy. Sounds great, right? Problem is, the whole point of this exercise was to detect spam, and we never detected any of the spams, right? Now, as an alternative, you could do the opposite. Well, classify everything as spam. The problem is that now you have a lot of non-spam email also classified. And so this is a quick example to indicate that accuracy may not be enough to understand the quality of a classifier in this case. And you may have already sort of sniffed that there was an issue actually with our data set construction, because you might say, well, that's kind of dumb. Why don't you just grab 50 emails that are spam and 50 that are ham, and then train the model with that instead? And if you give it 50-50, then something this naive wouldn't work, and maybe you can train it better. And even though, yes, that could be an approach, it turns out actually that this is a situation called class imbalance, where you're trying to classify, in this case, 2 classes, spam or ham, but the data you have is not evenly balanced. You have a lot more data about one class than the other. And this is actually not an uncommon problem. Spam is an example of a general class of classification problems where you're looking for rare events. Imagine you're part of the fraud department in a credit card company and you want to detect fraudulent credit card transactions. Turns out that most credit card transactions that people make are non-fraud. People just go about their lives and they shop and they buy stuff on Amazon or at the coffee shop or pay for their gas at the gas station. Most of that is plain vanilla stuff. So the vast majority of transactions are non-fraudulent. The problem is, the ones that matter are the small fraction of them that are fraudulent. And so in general, your training data is going to be imbalanced. And you don't want to say, well, if I only have these many of the things I have, then I'm only going to grab the same amount of the regular data, let's say, for training, because now your training data set becomes very, very small. So training in a scenario of class imbalance is challenging. We're not going to completely cover every approach available to tackle that issue, but at least we're going to study the notion of using more than one metric to think about your classifier in contexts such as this one. And so for that, we're going to introduce some notation. So you're going to see this kind of matrix, this kind of little table that we have here on the right quite a bit. This is known as a confusion matrix. And it is, you may see it displayed in this way or in its transpose. There's no universal standard. So in here we're constructing this matrix with predictions on the across the columns and the actual data across the rows. But you may see examples that use the opposite. And so whether you're reading a paper or using a computational package, you need to double check whether it's being shown, the confusion matrices that are being shown this way or in the transpose. But the point is, the concept obviously is the same regardless of how it's laid out. It is a way to think about the different types of error that you can make. So you imagine we have all of our data, and all of our data either is the actual data either belongs to class 0 or to class 1, meaning the actual value is either 0 or 1. And by the way, we're going to use the terms from now on: positive referring to 1 and negative referring to 0. Not that we're saying that 0 is a negative number. This is terminology that refers to basically how we're answering the question. Remember, our model is the probability of an observation being of class 1. And so positive and negative refers to, is the answer to that question a positive answer or a negative answer? Is the answer to that question yes or no? So the question is, what is the probability that this observation is class 1? Positive answer means yes, it is class 1. Negative answer means no, we're predicting it to be class 0. So obviously, for any observation, the data is either actually class 0 or class 1. And here, I want to remind you, the fact that we know this answer, the fact that we know what the actual label is what puts us in the realm of what we called in the previous lecture supervised learning. We know these answers. The only way we can build these tables and we can look at these quantities is because we know these answers. And this is why supervised learning gives us all of these techniques. If we are in a realm where we're making predictions about something but we don't actually know the answers, that's a different story, right? So this is connecting to the taxonomy we looked at in the previous lecture. And so we're going to define 4 quantities. Whether the prediction, given that the data was actually, let's say, class 0, that the true answer was negative, did we predict that the answer was negative, right? In that case, we call that prediction a true negative. It is negative, and we called it negative. This is what we call. This is what the data is. Now, if the data was if the true answer was a negative, but we called it a positive, that's called a false positive. This is like a false alarm, right? There wasn't anything there, but we said there was. So that's called a false positive. Now, the opposite is a false negative, when something is true, but we didn't call it to be class 1. We made the call that it was class 0. We answered the question in the negative, and that was a mistake. The answer was that it actually was class 1. And so this is when we failed to detect something, right? When, based on the notion that the question we're asking is this thing class 1? That's what we want to detect. Then this is an example of when we failed to do that. And finally, the case of a true positive is when the answer is that yes, the answer is a positive, and our answer is also a positive. So these are the 4 options, and based on these, we're going to define a few. First of all, let's take a look at how these can be visualized. So this is what the scikit-learn code for computing a confusion matrix produces. So based on our model, the confusion matrix method based on the data and our predictions, will produce an actual NumPy matrix with these data that we can visualize as what's called a heat map with Seaborn in a single function call. So this is an example of a situation where we have in here our true negatives, our true positives, and these are the false positives and the false negatives. In this case, it is laid out exactly according to our diagram here. As you can imagine, in general, what you're looking for is having most of your data here on the diagonal. You want mostly true negatives. You want to catch both true negatives and true positives with a minimal amount of data on the off diagonal elements. So based on these quantities, we define three different metrics. Accuracy is the one we've already talked about. This is the ratio of true positives plus true negatives. So it's the sum of the elements of the diagonal of the matrix divided by the total number of observations, divided by every possible data point, right? But as we saw already, it may not be, it's a useful quantity to think about, but not the whole story, especially in cases with high class imbalance. So this is where we introduce precision and recall, two other quantities computed from the same table. So precision is defined as the ratio between the true positives, right here, and the sum of the column elements, the sum of all predictions, the sum of true positives plus false positives. So the idea is, in here, computing the ratio by this ratio by penalizing mistakes we make by making false positive calls. So if you think about it, if you had no false positives at all, right, then precision would be 1 because it would be TP over TP. If this was 0, then precision would be 1. Now, any amount of false positives makes the denominator bigger than the numerator, which means that this will go below 1. So precision is a metric that is at most 1, but can go below 1. So having high precision means having this close to 1, but it goes below 1 by virtue of having false positives. So whenever you're in a situation where you want to minimize false positives, you're thinking, I want to maximize precision, right? Because precision is penalized, is hurt by false positives. Now, the alternate metric is to ask, well, what is the ratio of my true positives, but compared not to all of my predictions, but to all of the actual data. So instead of penalizing the true positives by the false positives, we penalize them by the false negatives. So in this case, what we're saying is if false negative rate was 0, then this recall would be 1. So recall and precision both are quantities whose maximum possible value is 1, but recall is penalized by having false negatives, right? So whenever you're in a situation where you're saying the cost of false negatives is my big problem, this is the quantity that I really want to keep under control, that's when you're saying I'm trying to maximize recall. And so one thing that I want to highlight as you think about these two is the fact that their denominators are, for precision, the denominator, the quantity that it is sort of fighting with, that your true positive rate is fighting with, is purely based on the predictions, meaning that precision is purely a property of your model, right? Whereas recall is a property that involves a lot about the data itself. I mean, obviously the model is there, but in terms of sort of your intuition is that precision is the behavior of your true positives relative to your own predictions, whereas recall is relative to the actual values in the data, because your denominator is taken from the row of the confusion matrix, if you will, under this layout, which is data driven, right? These are the actual values. This has nothing to do with the model. So having defined these two quantities, let's revisit our previous model, our previous example, where we talked about classifying emails as spam or ham. But now think for a moment about what is not just the accuracy for this one, if we go with our friend's naive classifier, but also what is the precision and recall for these. So I'm going to stop for a second, think about this, maybe grab a piece of paper and try to think what are, according to these definitions we just made, the values of accuracy, precision, and recall for this one. Well, we already know that accuracy is 95%. I'll assume you've paused the video. And now let's take a look at these quantities. So in our case, the true positive rate is going to be 0 because by definition we are calling everything ham. So so we'll never have a positive. The false positive rate, because we're never calling a positive, is also 0. And the true negative rate is 95, whereas the false negative rate are those 5 actual spam emails that we missed. So these are the 4 quantities in our confusion matrix for our very simplistic classifier. And this leads, if we just apply our definitions, to having 95% accuracy, but having 0 over 0 for precision, so it's undefined, and a recall of 0. Right? So this is a case where as we see, if nothing else, this should be an indicator that if we have 2 metrics that whose sort of optimal value from thinking about the quantities that describe them should be 1, and one of them is 0, and the other one is not even defined, then that's probably a sign that this notion that having 95% accuracy was a great model is probably missing something, right? That there's more to this story. And as we said, this is a particularly egregious case of a high class imbalance data situation coupled with a very naive model where you would need to do something else. So, and this is an illustration of the fact that in general there tends to be a little bit of a tension between precision and recall. Ideally, you would want them both to be perfectly 1, but you'll never be able to achieve that in practice. And in general, you tend to have to sort of work with your model to increase the quality of both of these at the same time. Because naive approaches, like saying, well, I could get recall to be 100%, if I make my classifier always output 1, if my predictions are always 1, then by construction, let's look at what recall is. Right? If we go to recall and our classifier always makes a prediction of 1, it never makes a prediction of 0, then by definition it can't have false negatives because it never predicts negative. So the false negative rate is by definition 0, and so this quantity becomes TP over TP, which is 1. But that's not a particularly useful way of reaching good of building a good model, because it's a model with terrible precision, right? If we have no false negatives, but there's going to be inherently any data point that wasn't actually that was actually a negative will not be detected as such. So we're going to have a huge false positive rate in general, given whatever is actually there in the data. So this is a very naive way of getting good recall, but by basically sacrificing precision altogether. Now, up until now, we've only discussed basically moving around the threshold. And obviously, if you think about these numbers, you can see that if you move your threshold higher in your classification model, you'll tend to have fewer false positives, right? Because by definition, the threshold, we're calling positive the one label. So if we move the threshold higher and higher, we're leaving fewer and fewer opportunities to have a positive. So if we have fewer positives, then by construction, fewer of them will be false positives. And conversely, if we lower the threshold, right, we will tend to have fewer false negatives because this will tend to increase our recall. So this is the knob that the threshold gives us as we move along our probability line, and the effect it has on these two. That is an indicator that playing with a threshold is probably not enough in the real world to solve modeling problems, because just moving the threshold around implies a fairly simplistic kind of trade-off between precision and recall. And since what you're trying to do is to actually improve both, in general, that can only be reached by, in addition to finding a good threshold, by improving the actual quality of the model, right? By actually basically working with your features. As we saw in the case of linear regression, it's the same thing. What kind of features do you have? What can your model actually learn from your data is what will allow you, for any given threshold, to improve the quality of both your precision and your recall. So finally, to gain a little bit of intuition on these, let's imagine three scenarios, and we've already mentioned that in modeling you may need to consider different trade-offs. Let's think about three concrete scenarios, and let's think what these metrics reflect in these scenarios. Imagine that you're trying to predict whether a patient has a disease or not based on some medical data that you have from them, tests that you ordered, for example, if you're a doctor. Or imagine that you're trying to decide whether someone should be sentenced to life in prison, and you want to do that in a data-driven fashion. This is a complex and controversial topic, but that is very much in the real world. There are algorithms that are used by the criminal justice system to make decisions about people's lives and about people's sentencing and bail and other aspects of criminal justice decisions. So let's think for a moment at least about these kinds of metrics and questions. And finally, our old spam and ham example. So stop for a second and try to think about these three metrics in the context of these examples and what kinds of trade-offs would matter for each of these. So, and I want to emphasize that this is only a starting point, because at least I'm going to give you a little bit more perspective in some of them. Ultimately, in each case, you will have to think long and hard about your model and about which metrics of your model are the ones that you choose to optimize and where you choose to drive it based on the actual decisions you'll be making in the end. But to first approximation, we can think that a case where we're looking at making a prediction on whether a patient has a disease or not, maybe one where recall is the metric that we want to maximize, because what in this case, presumably if the person has the disease, they will go through further testing, and what we don't want to do is send them back home where they may get sicker, and by the time we realize that they did have the disease, now it has progressed, it's later, treatment may be more complicated, more expensive, or they may have a worse outcome, whereas we're thinking, well, if we tell them that they have the disease, that worst case scenario, the next round of testing will tell us if we had missed something. That's a perfectly reasonable starting point to think about the cases like medical treatments, but it's not the end of the story, because you could also say, well, if this decision is a decision that I'm making at a point where the next step in their treatment would be to apply, for example, give them a medication that has very, very problematic and complicated side effects, and whose benefit is not completely clear, so it has very toxic side effects, but it may not actually help them all that much, you may actually make the opposite decision, and you may say, you know what, patients may be willing to actually not move forward. That's a classic example in situations like certain kinds of cancer chemotherapy or other drugs that are quite toxic, where you may actually think differently about these trade-offs. So I want to mention that simply to say these are not simple hard and fast rules where you say for medical treatments, recall maximization is the only thing that matters, box checked in your head. No, these are questions of trade-offs. They're questions of trade-offs, and trade-offs apply to every concrete situation in a different way. And even situations in the same realm, such as, say, medical treatment, are not all identical. So you need to understand what your trade-offs will be in any given scenario. Now let's briefly think about the other two cases. Criminal justice decisions. That might be a case where you want to maximize precision instead. In this situation, the cost of sending someone, say, to life in prison, and as in this case, the example we're using, is morally very high. And so this goes to kind of the old maxim about justice, that justice systems would rather see a guilty person go free than put an innocent person in prison. It's kind of one of these general maxims about justice, and that would be encoded by saying that you want to maximize precision. This is a case where you absolutely don't want to send someone to prison who is otherwise innocent, even if it does mean letting a criminal go free. And finally, the case of email is one where maybe accuracy is the metric that you want to optimize for. Even though, as we did see, it is a metric that paints an incomplete picture of the whole situation. And so you may want to look at sort of which other pieces of precision and recall you add in order to get a complete picture of that kind of model.